Okay, well, we're back, still talking about elastic potential energy. We're going to stick on that today because it's a new topic. So we're going to go slow, and another day talking about it will be good, especially if we do some examples together. So here's an example right here that we can think about. Let's say you have a wall here, okay? And then over here is this floor. And let's say, just for the sake of simplicity right now, that there's no friction. Mu k is equal to 0. And let's say attached to the wall is a spring. Here's the spring, and then we attach some mass to it, a box, a block, who knows. All right. And we are going to pull this box away from the rest position, which is right here. There's the rest position, x is equal to 0. And we're going to stretch the spring so that the box gets to here with a new position, which I'm going to call x initial of positive 0.03 meters. And this box has a mass of 2 kilograms. And I'm going to stretch it and pull it to here, and then I'm going to hold it here. So it has no velocity to begin with. I'm stretching it, pulling it, and holding it here. And as I'm stretching this box, this spring, which is attached to this box, I'm going to tell everybody here that the spring constant is 3.3 newtons per meter. So there it is. I pull it over to here. I've moved it by 0.03 meters. I'm holding it, and then boom, I release it. I release the box. And the spring is going to pull the box. So the box is going to start to move this way. Now, how fast will the box be moving when its new position, its final position, is 0.05 meters? That's what we want to calculate. Well, how could we do this? Well, we could do this in a way that's very similar to finding out if you have lifted up an object to some new height, right? And we hold that object, and with when initial velocity is 0, and then we drop it and we let it fall. And then we say, hey, how fast is this object moving when it's at this height? Oops, let me fix that. I shouldn't have put an F there. Question mark is better. How fast is it moving when it's here? So I lifted it up, held it at that height, released it, and it's falling. How fast is it moving here? So it's gravity that is pulling it back down. It's gravity that's restoring it to where it was initially. Well, it's very similar here. Instead of gravity, I have a spring. Instead of lifting an object through a height, I'm stretching a object attached to a spring. I'm holding it, and then I'm releasing it, and it's the spring that's bringing it back instead of gravity. But it's more similar than you might think to begin with, all right? So if we would have done this question here back in grade 11, we would have used the law of conservation of energy as one of the possible methods to find out where this object's, or what this object's velocity would be when it is at this new height. So let's use that same technique here. Let's say that the total energy final, which would be the energy of the object when it's here, drawn with dashed lines, and its position there is 0.05 meters away from the rest position. Its total energy there has to equal the total energy that it has when it was at its initial position right here, and it was being held. All right, so energy total final equals energy total initial. The energies at this point and the energies at that point. Well, now we need to break down these total energies. These total energies now are kinetic energy, so kinetic energy final, but we don't have gravitational potential energy here. It's on the floor, it's on the ground. but we do have elastic potential energy. So the total energy final is the sum of elastic energy final and kinetic energy final. And that's going to equal the total energy initial. And it is also the sum of the elastic energy and the kinetic energy, but in the initial situation. So elastic energy initial plus kinetic energy initial. But was it moving at the beginning? No, it wasn't moving at the beginning. Okay, so it had no kinetic energy at all at the beginning. So that term is eliminated, all right? And we want to find out how fast it's moving at the end. So what we're going to do is we're going to take this term here and bring it to the other side, but it becomes negative. So this equation becomes energy kinetic final is equal to energy elastic potential initial minus energy elastic potential final. So let's write out what these are. Kinetic energy final, half mass times final speed squared, is equal to elastic potential energy initial, which is half times the spring constant times the initial position squared, minus elastic potential energy final, which is half times the spring constant times the final position squared. All right. And what we're going to do is we can cancel out the half which is in front of each term. That cancels out. Then what else can I do? Well, I can factor out this k and this k, and it leaves me with k bracket x initial squared minus x final squared and bracket. I factored out the k. And the last thing I can do is I can divide both sides by m. So if I divide both sides by mass, it cancels out on this side, and it ends up in the denominator right there. Now, if I plug in all the numbers, I get an answer of 0.03 meters per second. So I have found how fast this object is moving. When I released it, it left its initial position and is now here. And we did this without considering any friction. Now, as an aside, an error that a lot of kids make, I have this aside right here. This is x initial squared minus x final squared, which I'm representing here. It does not equal x minus y within a bracket and then square it. No, you square it, and from that you subtract the other squared. Not you subtract them and then you square it. It's a very common mistake. Don't do that. All right? So let's make this more complex. I think that would be a good idea. What if there was a coefficient of friction of 0.1 in here? What would the final velocity be then? Let's try that. So, once again, we would use law of conservation of energy to solve this. So, energy total final is equal to energy total initial. The initial energy is all that elastic potential energy as someone is holding that mass at the end of the spring just about to release it. When the object gets to the new position, the final position, there'll be some elastic potential energy there. There'll be some kinetic energy there. It'll be moving, at least we think so. And there'll be some energy lost through friction, work thermal. We talked about that before. So let's write out the expressions for each of these. Here's the expression for elastic potential energy final, half kf squared. Excuse me, half kx f squared. Here is the kinetic energy for this, half mvf squared. So here are each of these described in their expressions. And then here we would have work thermal equals the force of kinetic friction times whatever displacement that object went through. And this is all in magnitude signs here, all in magnitude signs. We have to make sure we get a positive answer there. So we're looking to solve for this final velocity. That's what we want to solve for, the final velocity. So since we want to solve for the final velocity, we move this term and this term over to the other side. Okay, we move it to the other side, and here they are. And they both become negative. We moved them to the other side. Then the next thing that we're going to do here is multiply each term by 2. So I multiply that term by 2, the half is gone. Multiply that term by 2, the half is gone. Multiply that term by 2, the half is gone. And multiply this term by 2, and it remains since there's no half to cancel it out. The next thing we're going to do is divide each term by m. So if I divide this term by m, it cancels out. If I divide this term by m, there's an m in the denominator. If I divide this term by m, there's an m in the denominator. If I divide this term by m, there's an m in the denominator. Say that 5 times fast. And there we have it. Okay? We have the expression right here. Now, we have to put in here what the equation is for the force of kinetic friction. Right? Remember the equation for the force of kinetic friction? Looks like this. There you have it. Which we know in this situation, normal force is opposite in direction but equal in magnitude to the force of gravity. And we know what the force of gravity expression is. It's mg right there. So that's what I have. I have that right in here, right in there. Okay? So that's why this has been replaced. So what's the next thing I'm going to do? Well, I can cancel out an m there. That's gone. I'm going to drop the magnitude signs. As long as I substitute in positive values here, I can drop the magnitude signs. What else can I do? Well, I can factor out a km out of these first two terms, and that's what I've done. So I've factored out a km for these first two terms, and I've divided by m in the last term. And now I can substitute in the values. Okay, let's do that. I plug in all the numbers, and this is what I get. I get Vf squared is equal to negative 0.028 meters squared over seconds squared. Wait a second. I can't square root a negative number. No, you can't. So this is what we call an extraneous solution. And what it's telling you is that when you released that object, there was so much friction, it never got to that final point you were interested in investigating, the 0.015 meters away from the initial position. Let me show you where that is. It never made it to here. You released it from here, but the friction was so great and never got to there. That's why you got that extraneous solution. It makes no sense. You can't find the square root of a negative number. All right. So you might think, well, sir, this is kind of stupid. Why do we do all this? Well, we were able to make some sense out of this and find out that the object never got there. So that leads to the next question. How far did it get? Right? How far did it get? So we're going to repeat this. Okay, we're going to repeat this and say that the total energy it had at the beginning is equal to the total energy it had at the end. Now the total energy it had at the beginning was all elastic potential energy. It wasn't moving. And the total energy it has at the end will be by how much the spring is still stretched by. So it'll still have some elastic potential energy because the string will still be stretched. It would have overcome friction. But if that's as far as it got, the kinetic energy final, which you would think might be in there, is actually equal to 0. Remember what I'm asking here. How far did it get? So you release it, it slides for a certain amount, and it stops. It has no velocity there, therefore it has no kinetic energy there. So we're going to write out the expressions for these. Here is the expression for the elastic potential energy initial. Here's the expression for the elastic potential energy final. And here is the expression for the work done through friction. So this is energy lost, thermal energy lost through heat transfer. Remember, it's not moving at that point. So I work through this. And remember, we're trying to find how far it's gotten. What is its X final? That's what we're trying to find. Okay, don't forget that. And what we're going to do is Repeat this here, that stays the same. Repeat that here, that stays the same. We already figured out how to calculate the magnitude of the force of kinetic friction. But then I have to write an expression for what delta x is right here. And delta x is always x final minus x initial in magnitude signs here. All right? So since it's in magnitude signs, all right, I can drop the vector notation in the next line. It's gone. It's not there. What is left? Well, this is what we're going to do. We're going to try to solve for xf. But xf appears in a squared term and xf appeared in a non-squared term. When you see that and you're trying to solve for xf, what you're really trying to do here is use the quadratic formula to solve this. There's no other way around it. There's no other way around it. So this term stays right there. That term stays. This term, what I am going to do is multiply that into there, and it gives me this term right here. So there's your squared xf and your linear xf. And then I'm going to multiply that into there, and it gives me this term right here. And then where did I get this from? Well, it came from the other side. I brought it over, and it became negative. I've left this side 0 because I want to set it up in the standard ax squared plus bx plus c is equal to 0. I want to set that up like that. Then I can solve it as a quadratic. So this is what we have here. We have the 0. We're going to plug in all the values that we know. We're going to plug them all in here. That's what I've done. I've substituted. And it left me with this right here. Okay. Now, these values are so small, I'm just going to ignore it. I solve the quadratic formula, and it gives me that x final is negative 1.2 meters. Well, that makes no sense. That would say that the object moves past the rest position and gets all the way over into the negative x positions of a spring being compressed. That won't happen. That will not happen. Okay. What's the other solution? 0.029. So it started at a position of 0.03, and now it's at a position of 0.029. So what's that telling us is that when you released it, there was so much friction, it hardly moved. It moved a little bit. That's it. But you have calculated through using the law of conservation of energy where this object now is. Okay, so we've gone through this worked example today. Take a look at it. Make sure you did your homework from the post video that I made yesterday and the homework that I posted yesterday. Maybe with me going through these examples, it'll help you solve some of those problems there that you tried yesterday. At least I hope you tried yesterday. We'll go slow. We'll be patient with each other. If you have any questions, please post them in the discussion thread, and I'll answer them so the whole class can see your questions and the whole class can see my solutions. We're going to do the best we can. We'll get through as best we can. We'll be patient. We'll make mistakes. We'll forgive each other, and we'll get through. Okay? So have a good day. Bye.